So hi everyone, my name is Stefan. I'm from FOSSi Foundation, director there, and it's again a great opportunity to present you FOSSi Dial-Up, which is our usually monthly event that we have a very special edition today, which follows up on the presentations we had last year, if you remember, talking about the Skywater PDK shuttle. And today we will have some of the designers that submitted their designs there, which got successfully picked, and which are waiting for the silicon now. Maybe just as a reminder to everyone about FOSSi Dial-Up, the next one will be next week already. This is the regular edition. Currently, we have this topic around evolving communities, and Jonathan Balkind will talk about drawing open Python. And it will be next week at the same time. To learn more about for the activities of FOSSi Foundation, everything happening in the free and open source silicon community, and also about dial-up announcements, please subscribe to our newsletter, you can find it on our website. And today we'll have 4 presenters. We have pre-recorded presentations, so we will replay them, and then we will have quick interviews with them in the end. If you have any questions, please ask them in the chat, and I will follow up them after each presentation, and we will have a closing round in the end where we can discuss the experiences that everyone made. So the first one will be Midterm. He did a very nice project where he used many projects and created a multi-project harness. Steve Kelly will talk about RepCore, Tristan Gingold about OpenTDC, and Vladimir Milovanovic presents 2 projects that he got successfully submitted, which is, I think, a really great thing. Also with me today is Mohamed Kassem, the CEO of eFabless. How are you?
I'm very good, thank you. Thank you, Stefan.
Great that you're here today. You will join me, I think, during the interviews from time to time, and also in the end, in the follow-up round. There's the next MPW coming, right, this week?
Yep, the deadline is a few days away.
Awesome. So we will put the link during the presentation. I have to look it up, to be honest. And we will show it. We will put it on the YouTube comments and in the description below. Still a couple of days to go. I think it's very easy nowadays to build a ship, from what I heard last year. So a couple of days is hopefully enough to get your design ready to be submitted to the next MPW, right?
Yes, and then it's also important to say that if you go to the eFabless website and you find right now there are 44 submissions, that doesn't mean that it's already closed. So please do not hesitate to submit the designs and without any assumptions. And I'm excited to be here today to witness also the presentations by the team members or community members that have actually done the work on MPW-ONE and presenting their own experiences.
Awesome. So let's jump into the first presentation. Matt Wen talking about the multi-project harness. See you later, Mohamed.
See you.
Worked with FPGAs before, but never with ASICs, so this was my first experience with that. I saw Tim Edwards' presentation at WASH about using Qflow as an open source ASIC flow, and that got me interested in the process. So I started looking at it, and then Tim Ansell made the announcement that Google were going to be sponsoring some ASIC shuttles, and there was this new set of tools called OpenLane. So I was already looking into it, and I just jumped on board. I already had some FPGA projects that I'd used as learning projects, so I decided to use that and concentrate more on the ASIC side than the digital design side. So I used my VGA clock, a WS2812 LED driver, and a really tiny demo of a 7-segment driver. Once I started using the OpenLane tools, I realized how small these designs actually got in terms of the space that we have available on the shuttle. So I asked some friends if they wanted to put any
Hi, welcome back everyone. Sorry. Minor technical hiccup, meaning my computer got overheated and just turned off entirely, and I was playing from local. So let's jump back into it. Sorry for the inconvenience. I'm hoping I'm back on YouTube soon. The second. So let's.
My first tape out. I've done plenty of electronics.
So it seems it's working. So let's continue.
This was my first tape out. I've done plenty of electronics and some work with FPGAs before, but never with ASICs, so this was my first experience with that. I saw Tim Edwards' presentation at WASH about using Qflow as an open source ASIC flow, and that got me interested in the process. So I started looking at it, and then Tim Ansell made the announcement that Google were going to be sponsoring some ASIC shuttles, and there was this new set of tools called OpenLane. So I was already looking into it, and I just jumped on board. I already had some FPGA projects that I'd used as learning projects, so I decided to use that and concentrate more on the ASIC side than the digital design side. So I used my VGA clock, a WS2812 LED driver, and a really tiny demo of a 7-segment driver. Once I started using the OpenLane tools, I realized how small these designs actually got in terms of the space that we have available on the shuttle. So I asked some friends if they wanted to put any designs in together, and we would do a group application. So we put all those designs together, and it came out looking a bit like this. Eight designs that all get muxed together, and then we have the firmware on the Pico RV32 choosing which design is active at any point. Here's the 7-segment demo, the WS2812 driver, the VGA clock, and then from Richard, Spynet, Michael Betts and Ramsey Vittler, ASIC frequency, Guillaume Cabot, ASIC watch, Q3K, the reverse engineering TPM 2137, and Alexander did a HDMI driver. And this is how we muxed it together. So the projects come in here, they all go into a mux and out to the GPIO, and then we have the firmware on the system on chip, Pico RV32, choosing which of the projects is active. The easy part for me was taking the HDL designs and then hardening them with OpenLane to get the GDS macros. The hard part was putting all those macros together. OpenLane makes it easy to put all the Verilog or all the HDL into one big design and then harden that, put it into the Caravelle wrapper and submit it. But what I really wanted to do was keep all these little macro blocks separate and then harden them all together. If we'd have taken all the designs, put them into one big Verilog design and then hardened that, that would have been a lot more straightforward. But I was already thinking that I wanted to do a course and have people do the whole process themselves, harden their design into a small block, and then that is their block that they send to me, and then we wire it all together. And because of the way the power system works with Caravelle and OpenLane, every time you go down one level in the macro, you lose a layer that you can root on because you need to use the layer above to do the power. So going back to the mux idea, what I hadn't realized is that because there's no logic, synthesizable logic allowed in the user project wrapper, and that's the part that we can modify in Caravelle, all the mux logic had to be outside. But to instantiate everything has to be instantiated inside the user project wrapper. So what we had to do is route all the wires from all the projects into the user project wrapper and then back out to the mux and then out to the IOs. So there's a lot more wires than there should be. So when I get my first chip Matt, and this was my first tape out. I've done plenty of electronics and some work with FPGAs before, but never with ASICs, so this was my first experience with that. I saw Tim Edwards' presentation at WASH about using Qflow as an open source ASIC flow, and that got me interested in the process. So I started looking at it, and then Tim Ansell made the announcement that Google were going to be sponsoring some ASIC shuttles, and there was this new set of tools called OpenLane. So I was already looking into it and I just jumped on board. I already had some FPGA projects that I'd used as learning projects, so I decided to use that and concentrate more on the ASIC side than the digital design side. So I used my VGA clock, a WS2812 LED driver, and a really tiny demo of a 7-segment driver. Once I started using the OpenLane tools, I realized how small these designs actually got in terms of the space that we have available on the shuttle. So I asked some friends if they wanted to put any designs in together, and we would do a group application. So we put all those designs together and it came out looking a bit like this. Eight designs that all get muxed together, and then we have the firmware on the Pico RV32 choosing which design is active at any point. Here's the 7-segment demo, the WS2812 driver, the VGA clock, and then from Richard, Spynet, Michael Betts and Vamsi Vittler, ASIC frequency, Guillaume Cabot, ASIC watch, Q3K, the reverse engineering TPM 2137, and Alexander did a HDMI driver. And this is how we muxed it together. So the projects come in here, they all go into a mux and out to the GPIO, and then we have the firmware on the system on chip, Pico RV32, choosing which of the projects is active. The easy part for me was taking the HDL designs and then hardening them with OpenLane to get the GDS macros. The hard part was putting all those macros together. OpenLane makes it easy to put all the Verilog or all the HDL into one big design and then harden that, put it into the Caravelle wrapper and submit it. But what I really wanted to do was keep all these little macro blocks separate and then harden them all together. If we'd have taken all the designs, put them into one big Verilog design and then hardened that, that would have been a lot more straightforward. But I was already thinking that I wanted to do a course and have people do the whole process themselves, harden their design into a small block, and then that is their block that they send to me, and then we wire it all together. And because of the way the power system works with Caravelle and OpenLane, every time you go down one level in the macro, you lose a layer that you can root on because you need to use the layer above to do the power. So going back to the mux idea, what I hadn't realized is that because there's no logic, synthesizable logic allowed in the user project wrapper, and that's the part that we can modify in Caravelle, all the mux logic had to be outside. But to instantiate everything has to be instantiated inside the user project wrapper. So what we had to do is route all the wires from all the projects into the user project wrapper and then back out to the mux and then out to the IOs. So there's a lot more wires than there should be. So when I get my first chips back, I'm planning to make a circuit board to test out the WS2812 driver, or I might use the one that eFabless provides for that. I'll make a very small circuit board, the smallest I can, just with the ASIC and the flash for the Pico RV32 to load up and configure the IOs, and a VGA plug so that I can just plug that into the back of a monitor and get my VGA clock working on this tiny little PCB. I'll be sending some samples to the other participants, the 5 other people that submitted on my group application. And I'm going to be sending some samples to Mikhail from Zeptobars and John McMasters to do some decapping and hopefully get some really nice looking micro photographs back. My next steps are to continue running the course, to work on my second submission. So I've updated my mux idea. So instead of muxing, now I'm joining all the outputs and inputs together into one big bus and tri-stating the outputs. So if one project's got a problem, it doesn't ruin the other projects. And then the firmware controls which active line is active that allows the project to take control of the output pins. And I have some tools, the multi-project tools, which also are available for anyone to use. They're available on an open source license, the same as all the submissions are. And it automatically generates the config you need to harden all these separate designs into one big design that you can then submit to eFabless. So I've got my 2 demo designs from the course, which are an RGB mixer with PWM and digital encoders, and a frequency counter with a 7-segment display output of what the frequency is. And we're so far up to 5 contributions from the course, and I'm hoping to fill up the rest of those 16 slots with other contributions to the course before we get to the June the 18th deadline. That's it from me. I'm really happy to have had the opportunity to experience this and to hopefully pass the experience on to other people. And I want to say thanks to eFabless and the team there, everybody on the Slack that really helped pull together to get the first submissions in. It was a really difficult journey for a lot of us. And I especially want to say thanks out to Ahmed and Amma, who were on the eFabless team on the first shuttle, and they did a really great job with assisting us. What are you waiting for? Get involved and get a submission on the second shuttle before the June the 18th deadline.
This position you're in, right? Matt, you're muted, by the way.
Yeah, there we go.
No, you're unmuted. Yeah, you were frozen. But you're still in the same position. We could have a smooth transition, right? Speaking of smooth, sorry for the inconveniences. My computer just dies constantly of heat. It's 28 degrees in my office now, which is probably the reason. Yeah, sorry, everyone. I think we sorted it out. Matt, thanks for the great presentation. I think it's very interesting that you are like a newcomer, kind of, right? And I think you have the ideal situation to run such a course because you went to the same troubles, right? Learning it. And like, so what's your experience? Like, how much like efforts, learning time, also how steep is the curve? Like, how much do you think is 0 to ASIC? Like, how many hours, days, weeks, months for you?
Well, like I said in the video, I'd already done some FPGA stuff, so I didn't have to go through all the digital design stuff. I just had to go through OpenLane and the submission process. And for MPW-ONE, that was quite a challenge because there was a lot of churn in the tools at the time. And we're all like, some stuff would work for some people and then not another, and you'd find out you were on the wrong commit and this submodule wasn't updated and that thing wasn't working with this, and it was difficult to keep everything together. For MPW-2, it's been so much smoother. So I'd say that if you have like a medium-sized digital design, you could go all the way through to getting a GDS with like relatively easily. But then if you could run into corner cases, like maybe your design needs SRAM, and that's still quite tricky to get in. So then you're kind of using DFF RAM, which is then much bigger, and then maybe your design doesn't fit. So then you run into these issues, and then you basically have to like wade into the Skywater Slack and ask people how it's going, look at previous submissions. But that's another good thing to mention, actually, is that a lot of stuff has already been done on MPW-ONE, so you can see how other people have already done it.
So are you preparing for receiving the chips in terms of your electrical setup? I think there are quite a lot of questions around solder paste already, etc.
Yeah, I've done some BGA work before, and I'm not that scared of it. I think the most similar thing I've done is HyperRAM, which is like about the same size die, but, well, same size chip, but wider ball spacing. Yeah, but you know, for the first run, I'm going to have like 50 chips, and I only submitted with 5 other people, so I've got like chips to burn. But for MPW-2, we've got 14 other people on the application. So then I've only got like 2 or 3 chips per person. So I hope to work out my process on MPW-ONE, and then for the MPW-2 chips, there'll be less wastage.
Interesting. Yeah, I think it will be interesting to see like coming out of this, because like people that if you're not regularly doing this, it's kind of interesting, right? Because I think it's slightly different from what you're receiving from Mauser, right? Like getting like a raw chip that you built yourself, right? It's a little bit I think it feels different. Like you're more careful, etc. So if you have a look now, and there's like other people that also submitted their designs, how was the testing done on your side, right? So I think you have some trust that what you receive back works, right? But have you tried
I mean,
the test patterns for all the designs in it, or?
We've seen that eFabulous have done some tests that have come back unworking. So we know that Caravol works and that the SRAM works and bits and pieces like this. But we're waiting for MPW-ONE to come back in August, I think, is the latest update.
Okay. So August is the time frame. Yeah, that's great. So do you have like test patterns for the individual designs, and then you're doing the switching, or how did you test it?
Yeah, so every design has its own test bench, and that runs like separately for the design, and then also we have like a bit of firmware that sets the GPIOs up. So the absolute minimum you need is a bit of firmware on the Pico RV32 that sets the inputs to be in or out, or pull up high or low, or whatever tri-state, and then set up the clock. There's like a something like a PLL. It's apparently not a true PLL, but you can generate other clock frequencies inside. Set that all up, and then maybe your design just goes off on its own. And I did some testing of the whole thing on an FPGA. I mean, without like some of the custom stuff, but with the Pico RV32 and the multiplex designs.
Okay, great. Thank you very much. So let's jump into the next presentation. It's from Steve Kelly. He will present the RepCore, and we'll have a quick chat afterwards. Thank you.
Hi, I'm Steve Kelly. I'm going to be talking about the Robotic Application Processing Cores project, or RAP-Cores for short. The purpose of the RAP-Cores project is to implement open source motor control systems. And we're starting with the fundamentals. So we've divided it into two sections of digital control and analog design. So we're focused on both implementing the fundamental control algorithms for closed loop and designing the power circuitry to actually sense the motor. The target application for these things are robotics, CNCs, and 3D printers, and potentially other applications. Motor control in a nutshell is two elements, a control logic element and a power electronic element. We do our control logic on FPGA and ASIC, and we're implementing power electronics also on ASIC or from discretes on a circuit board. This system involves many sensors, some current sensors, some voltage sensors, and encoders. And our idea of the control system is pull all this together in a way that gives us good control and rich dynamics for the system. So why would we implement RAP-Cores in gates and hardware when there's many good microcontroller-based solutions available? One of the purposes of RAP-Cores is to allow scaling and better telemetry. So most of the microcontroller solutions that have rich telemetry only can control one or two motors. By doing this in digital logic, we preserve a lot of the bandwidth while giving us additional control of axes. It also gives us timing precision and ability to treat the motor more as a sensor because we're doing these low-level controllers at the bridge level. Now I have a picture here of the Mars rover because it shows in these types of robotic systems you might have several different types of disjoint actuators, such as a phased array gimbal, wheels for the rover, the camera gimbal, and the robotic arm. So all these need to be fused together in a way that you have a full picture of the collective dynamics of the system and not just one component. So by focusing on digital logic design and doing our elements targeting silicon, we maintain a pathway to ASIC, and we give ourselves a sliding scale on cost to capabilities because there's many different types of motors and all different sizes that we might want to drive. So for some small applications, we may be able to integrate bridge into an ASIC, whereas for large applications, we need to have them separate. So we maintain this ability to change our deployment while maintaining the same common control algorithms. And on the logic design, we're focused on increasing bandwidth and communication for telemetry. So part of this involves taking some of the sensitive timing of the kinematics and moving that to FPGA. So we have movement interpolators in addition to actual low-level commutators in our project. And this will allow for dynamics-aware path planning. So you can actually measure torques and measure how the motor is behaving and how it's interfacing with the environment, and then use that to change your accelerations or your objectives as you move around. At present, we're using YOSYS and NextPNR for our FPGA deployments, and we support 4 architectures. We did our first ASIC deployment on Skywater 130 nanometer process on the Open MPW Shuttle in December. We have a growing list of control techniques we're developing, and we have some development hardware that should be expected in the next couple months. We're focused on C binding, so we're targeting Linux and Arduino applications, so this will eventually allow interfaces from ROS and common CNC and 3D printer path planners, such as Marlin and TinyG and SmoothieWin. Here you can see our first deployment on the Caravelle chip on the left. So this includes the RISC-V microcontroller and our onboard commutator and encoder code in wrap cores. It's a little box in the area. This is a single channel version, but since we should be able to interface with Wishbone and control multiple motors, up to 4 likely on the Caravelle platform in the next couple months. On the right is a discrete level bridge design we've been working on for prototyping out the actual drive and power circuitry for our motor controllers. So we're asked to speak a little bit about the challenges we had with our first ASIC experience. So to be clear, our team comes from a lot of different backgrounds. Personally, I'm a math guy. I spent a lot of time in computational geometry. So switching to Verilog and implementing digital logic, I was very new, maybe had about a couple months experience. We did have some challenges along the way, more specific. So the gate level simulation was very difficult for us to get to. It turns out that we had been testing mostly on YOSYS, and we had a lot of compatibility issues with iVerilog. So the learning point from that was we need to test on multiple Verilog front ends. We also had several dangling asynchronous and synchronous issues and memory initializations that just go by fine on FPGA, but really do not work in ASIC. So we had to detect those. OpenLane was quite a pleasant experience to use. It really worked well. It started making a lot of sense. There was a lot of diagnostics coming out of it, so it made it really easy to iterate and learn. And I highly recommend just diving into the source code, looking at the synthesis scripts. It's very understandable, and you can learn a lot from it. So we deployed our first ASIC in December, and we're looking to get it back and validate the hardware. And we're planning to participate in future runs. To get there, we would need to ideally interface with the Wishbone bus. So this will help give us high bandwidth telemetry off our controllers. And we're going to continue to work towards analog design. Now, there's a lot of very interesting macros and components people are developing on the Skywater platform, and we're looking to integrate those in. And we're also looking to continue our work towards formally verifying the wrap cores chip using the Symbiosis and TabbyCAD toolset. In conclusion, I want to thank the open source community for starting a lot of this work in digital logic design and having such great open source tools available, eFabless and Google for sponsoring and developing the Skywater Shuttle. I think it's truly amazing that somebody like myself that had little to no experience in digital logic design was able to take my existing software development skills and move them into this world where now we're creating ASICs. I think this is just so cool and so exciting, and we're all thrilled to be a part of it. So if you're interested in participating in the project or reading more, or even using our cores in your Open MPW projects, you can check us out at rapcores.org or github.com/rapcores. We are all on the Slack channel, so you can reach out to us there as well. Thank you.
No, thank you very much, Steve. Thank you very much.
Thank you.
Thanks also for playing back from your side. Good experience now. Yeah, great thing. I really enjoyed that. It seems like you're actually building it as part of a larger ambition, right? So I'm wondering, like, are you planning to actually use it, or was it more like an experiment to you? Like, are you already sold on using it?
Yeah, so there's a bit of a background here. Our team is very involved in 3D printing. We all go back to the days of the RepRap project. So that's where we kind of got the RapCores name from, or inspired, the acronym. So yeah, we're supported and sponsored by some big 3D printing manufacturers. So we see this as kind of like the next gen in cost to capabilities and trying to improve 3D printing. So it's a real early R&D initiative.
Yeah, interesting. Yeah. So I think that's one of the interesting things, right? That you see some potential for innovations, right? And you can just like experiment, and even if you're not lucky to get on a shuttle, like you can try the next one, or like it's more accessible nowadays. Have you done other tape outs? Like probably yes, right?
No, I'm completely new to Verilog. I started in about like June of last year. I really until then I was doing numerical computing on like big computers.
Nice. So you learned digital design, Verilog, and tape out within a couple of months, right? It was November, I think, to that line.
The ultimate crash course, yeah.
So how was the experience, like coming from an entirely different background? Like it feels more accessible than it used to, right? From my perspective, but I don't know the outside world. Is it still like the scary stuff, or is it more accessible compared to software nowadays?
I think the power of it being open source was, the diagnostics that were coming out of it were kind of guiding us, like, oh, you need to fix this. Something's wrong here. Your density is too high, or your density is wrong. And we were able to really iterate. So I think OpenLane really was a good experience for somebody that hasn't done Cadence or any professional tools. I'm a developer though, so I kind of was able to understand the Tickle and the C and the Python and just try to figure out how it's all strung together. And
so the Tickle is still there, right?
yeah.
That's still part of it. There's a question from the audience. So it is: have you implemented power transistors? I don't think there's any that come with the PDK, right? Did you have to do anything around that, or?
I think there might be a 20 volt version. That might be a little bit low for what we need for 3D printing, because most of those are doing 24, maybe even 36 volts. So I know we're kind of in we're focused on the digital logic for ASIC, and we're doing the power on discrete on board, and then we'll try to migrate that as we see that ecosystem develop, and we can try to ADCs and things like that. There's a lot that's on the MPW-2 that will be really useful for us down the line.
So you're probably looking for collaborators that are deep into analog and power, right? So
yeah, for sure.
Very would like to get in touch with you. The other question is if you plan to add it to LightX. I don't know. Do you know LightX? It's just,
yeah, we're quite familiar. Right now, our source is in Verilog. We are looking to do SoC deployment. So we've had a big project the past few months to try to get a working Wishbone bus, because right now we use SPI as a primary bus to interface with microcontrollers, because that's pretty universal. But we are realizing there's a lot of value in these kind of, Pico RV32 with some motor controllers. We do need a lot more processing for 3D printing, though. We need like floating point units and things like that. So it's unsure, it's more of a future focused thing.
Okay. So do you think you can evolve with the current conditions? Like an FPU is probably still possible in this area, right? Do you know like how much area did you use in the end for design?
I think we were like 0.6 or 0.8 millimeters squared or something. I mean, very, very tiny, and that was a single axis. We can do more axis now. So we have like, 4 and 8 axis systems that all use the same resources and interpolators.
Nice. It's very interesting. Like, it's really good to see that you're not designing for the purpose of designing, which is my approach usually, but actually for an actual project, right? That's really interesting to see. Awesome. Thank you very much.
Thank you.
So we will see us later. The next presenter is Tristan Kingold. He's working for CERN and he's doing some physics there, which is also, again, like a really applied use case. So let's jump over.
Welcome to my presentation of OpenTDC. So my design is composed of many TDC and fine delay. A TDC is a time to digital conversion. So it's a simple device that timestamp a pulse. And fine delay is the opposite. So it generates a pulse at a given timestamp. These devices are used in the high energy physics, mainly to measure time of flight. But it can also be used to replicate the signal. So you first timestamp and then you generate at different places. Or to also to measure any reflection. So time to digital converter timestamp a pulse using the frequency of a clock. So in this example, you have a pulse in the lower wire, which is sample as 1 at edge 7, so you know that the cycle is 7. But what you want with the TDC is to have a better precision than the clock frequency. And in order to get a better precision, you use delay lines, which are made of delay element and of flip-flops. And when you detect a rising edge of a pulse, you sample and detect the first delay element, which is set to 1. And using this trick, you get subcycle precision with the precision of a delay element. For fine delay, so you have to generate a pulse or ramp as at a defined clock edge, and for that you use a timer for the cycle, and you also use a delay line composed of delay element to get subcycle precision. My main objective for the design was to be digital only. I didn't want to design an analog cell because I am not an analog designer. So first, I wanted to get at ease with the open lane toolchain. And because I didn't have any existing design to harden, I tried to write and to design something which is quite simple, so no highly complicated logic. And also an objective was not to create a design that could have been a simple FPGA design. And I also wanted to test various implementation of my design, so trying various technology of various layouts. So this is what I choose: fine delay and TDC. And in my design, there are many TDC and fine delays. It is composed of many macro and even some macro. So at the end, I have almost 50 macro blocks. And some of the macro, in particular the delay lines, are directly generated by a small script. It also uses several libraries in order to test performance of them and how they behave. So I use high density, high speed, and medium density. I wanted to use OSU, but at the end it didn't work that well with the current tool. Maybe I think it has improved. Also, my design is completely written in VHDL. There is almost no Verilog in it, at least for the input. and it is made in a safe or resilient way. So if some element fail, I still should be able to use the remaining of the design. So this is a block view of my design. And with some explanation, it's a little bit easier to understand. So there is the main block, which is connected to the wishbone interface of Caravelle and has many subblocks connected to it, and it propagates the bus to different extenders, to which there are also blocks attached. The top level is composed only of macro and wires and strip lines in order to be quick to route. And there is also the clock distribution element, which try to distribute evenly the clock. In addition to this main design, there is also a completely independent block, TDC and fine delay, which is attached to the debug lines of Caravelle. And the idea that if anything goes very wrong in the main design, I can still use this what I call the rescue block. So why did I use so many macro? There are two main reasons. The first reason is a practical one. It's designing and placing and routing a macro. It's much faster than if you have to place and route the whole design. A macro is placed and route in I would say about 1 minute, which is quite fast. And when it's done, when it's hardened, I just have to place the macro. The main drawback is that the timing is not completely sure, because the timing analyzer doesn't handle macro very well. The second reason is that for the delay lines, I wanted to have a very regular structure in order to have a good precision and a good linear output from the delay line. So I wanted to have almost the same delay between each delay element, the same length of wire between each delay element. Most of the delay lines are placed by a script, so it directly generates a DEF file, and then they are routed normally with OpenRoute. And then these macro are manually placed in the upper level block. So this script will generate delay lines, taking as a parameter the technology used, which delay cell is used for the delay, and the length of the delay line. So it's either the number of elements, or here it's logarithm of the number of elements. So this is an example of a fine delay block. So it is composed of 3 different delay lines. So there are 3 in order to be able to calibrate a delay line. So there is a reference 1, the 1 which and 2 which are used to measure the 2 different inputs. So there are delay lines and all the logic required to get the value from the delay line, to connect the delay line to the wishbone bus. And what was difficult in design is to be able to place correctly the sub macro in order to have a macro which is working correctly. As another example, there is a TDC macro block, which is also composed of 2 delay lines with flip-flop and a lot of logic. The main difficulty with macro is power distribution. So I use 2 different strategies. The first one is the recommended one, where you let the horizontal strip line from the design to run over the macro, and in the macro you use a vertical strip line for power distribution. This has few constraints than the other strategy, but it reserves the layer, one layer in the macro, so you cannot route any signal in the macro on the same layer as the horizontal strip line of the design. The other strategy, which is first I tried, is to use the same horizontal strip line in the design and in the macro. This is a little bit difficult because you have to be sure that the stride is the same in the design and in the macro, and it constrains the size of the macro because it has to span at least 2 different strip lines, power and ground, and you cannot place easily the macro because it has to be on the same strip line. But you can use the horizontal layer in the macro, so you have more layer to route in the macro. What do I plan to do when I get the chip? I want just to test the design to be sure it works, and then to measure the stability and precision and noise I get in the current implementation, and to measure across all the various blocks I did. In a future implementation, I think I will have to do some analog design in order to improve the pad or to improve the delay element. I also wanted to test other library like the OSU1, and possibly to use RAM in order to handle burst of pulses and to keep the timestamp, to save the timestamp into the RAM. Thank you for your attention.
Thank you, Tristan. Thanks for the
You're welcome.
So for me, to be honest, like when you introduced, I don't know anything about analog, it sounded so analog, everything, but that's what borderlines, right? It's like interesting to see like what you can do with digital. I'm wondering what's the time scales you're talking here, right? So it's pretty down to the granularity that you can actually see, right?
So you mean the precision of the?
Yeah, the precision for the pulses.
I think it's about 100 of picoseconds measured by timing analyzer. But that's something also I have to measure when I will get the chip.
It brings immediately to the question that I also had, like, how do you really do the measurements for calibration? It usually, I think it's a complicated setup, right? When you want to really also see the contributions of pad and the macros, etc., right?
That will be something that's a bit fun, yes.
Okay.
So the idea is that I have a design is replicated multiple times in order to try to avoid external noise or perturbation, and I will hope to get the best result out of that.
It's interesting. So you would run like repeating tests with different chips, different macros.
Yeah.
If the expectation works. So could you simulate it before? Like, were you able to simulate it in a way?
Yes, I did a couple of simulations. It was not very easy, but at least I know it should work. I don't know exactly the performance of it, but that we will see that.
Right. What would like the performance characteristic be? Like, how do you measure it? It's like the precision or like the
Yeah,
detail?
I'm mostly interested in first precision and second the stability, in particular with the temperature variation. That's something. Okay, usually you should be able to have a good estimation of precision with tools like SPICE, except that SPICE works well when the design is quite small, and this is not exactly anymore a small design. And SPICE doesn't allow you to know how it will behave with variation of temperature. But you can set the temperature in SPICE, but you don't know exactly how the temperature will evolve in your design. So I'm not sure what could have get with SPICE.
So would you need kind of sensoring to calibrate at runtime then, or?
No, I don't think there is no way to do calibration at runtime. Well, you can at any time when you do a measure, you can also measure an internal delay. So you could be able to modify your measure with what you get from the reference delay.
Awesome. Right. So, and then there's some practical application, right? So are you planning, like it's an R&D project, obviously, but is there like a plan that you actually can use the design later on then?
I think as an application, I'd like to try to measure the echo of a laser or something like that. Maybe you should be able. Ideally, you should be able to measure the distance of between two objects using laser and reflection, the time of flight of the laser.
Interesting. So someone was confused now. So what are you trying to measure? The length of pulse or time of arrival or both?
No, the time of arrival. So you saw the pulse. You know that the pulse has started, and you measure the time of what the laser is received back.
Awesome. Thank you very much. See you in the final round. We have the last presentation for today. Thanks a lot. It's by Vladimir Milovanovic. And
hi, everyone. I will be presenting our experiences and impressions from the first Skywater Open Source PDK Shuttle, to which we have submitted 2 projects named Spectrometer and Lin Sorter. My name is Vladimir Milovanovic. I'm an assistant professor of electrical engineering and computer science at one of the local universities. And I'm also leading a small IC SOC design team of young engineers in a local company. Our long-term goal is to build a versatile radar signal processing accelerator that will be able to work in real time. The whole thing is still far away, but bits and pieces of that are already there. So once we heard about this open source shuttle, we decided to set ourselves a milestone to fabricate what we have and improve from there and learn from that experience. Well, we didn't want to send just the building blocks. We wanted to create some small systems, as small as possible, but nevertheless systems. So the question was, what system can we assemble from an existing Hi everyone. I will be presenting our experiences and impressions from the first Skywater Open Source PDK Shuttle, to which we have submitted 2 projects named Spectrometer and Lin Sorter. My name is Vladimir Milovanovic. I'm an assistant professor of electrical engineering and computer science at one of the local universities. And I'm also leading a small IC SOC design team of young engineers in a local company. Our long-term goal is to build a versatile radar signal processing accelerator that will be able to work in real time. The whole thing is still far away, but bits and pieces of that are already there. So once we heard about this open source shuttle, we decided to set ourselves a milestone to fabricate what we have and improve from there and learn from that experience. Well, we didn't want to send just the building blocks. We wanted to create some small systems, as small as possible, but nevertheless systems. So the question was, what system can we assemble from an existing building blocks? For example, we had an FFT. FFT is a central part of a spectrometer or spectrum analyzer. So we decided to build that one. For the second project, we simply used an approach that if someone else doesn't want those precious 10 square millimeters of silicon, we'll jump in and take it over for us. So the bottom line is that both Spectrometer and Lin Sorter projects are actually just a tiny part of a much larger picture. How we managed to submit 2 projects? Well, that's because we are leveraging agile chip design methodology through parameterizable generators that are written in Chisel, hardware design language, which is relatively modern. It is embedded in Scala programming language. It is intended or tailored so that one can easily write parameterizable circuit generators, which are then emitting synthesizable Verilog code for certain parameter sets. So this generator methodology enabled the creation of reusable components and libraries, just like in software we are using that, just this is hardware. So we've made FFT processor, sorting accelerator, numerically controlled oscillator, and this enabled us to raise the level of abstraction while still retaining the fine-grained control over design details that any HDL, standard HDL provides. So let's see, what is a spectrometer, just briefly. It's a scientific instrument that is used to separate and measure spectral components of a physical phenomenon. To that end, it is similar to spectrum analyzers, electrical equipment which measures magnitude of an input electrical signal versus frequency, or its digitized version, which is, for example, shown, the plot of spectral analyzer is shown in this graph over here. This analysis and conversion from time domain samples and temporal data to frequency domain spectral data is often done using fast Fourier transform, which is a central part of digital spectrometer backend that we are proposing. So this is the block level schematic of the spectrometer. In the center is the FFT. It produces the real and imaginary part of the spectrum, from which we are taking magnitude or magnitude squared or logarithm of that magnitude. And if we want to reduce noise, we are accumulating those spectral components for multiple times. Since there were no data converters nor high-speed serial interfaces available for this first shuttle, we integrated a primitive built-in self-test capability to characterize the spectrometer with this numerically controlled oscillator. So let's go to the FFT generator. The topology we chose is a single path delay feedback FFT processor. It allows us streaming manner, so on every clock cycle we can have a new in-phase and quadrature data points in fixed point integer, and we can output the spectral components after certain latency. We can use either radix 2 or radix 2 squared topologies with decimation in time or decimation in frequency. For this, our instances had radix 2 squared with full runtime configurability, and decimation in frequency was used where this bit reversal or descrambling was done in the accumulator here. We also have some implementation specific parameters, like these delay cells can be implemented either using shift registers or block RAM or SRAM cells, depending whether we are implementing this on FPGA or ASIC. The input is XE4 stream with standard ready valid handshaking. The output also, and the configuration of this core, runtime configurability of this core is achieved through writing and reading these control and status registers through bus, which is also a parameter in our design, and it can be tiling, XE4, APB, or AHB. For this instance, we have chosen XE4. So any power of 2 length FFT can be supported in this way. How do we provide these input data? Well, we use a numerically controlled oscillator generator, which gives a nice sine and cosine wave. It is just a phase accumulator, which is cascaded with a sine cosine lookup table. To improve spurious free dynamic range, it uses some techniques like Taylor series correction or dithering. We can do frequency and phase modulation using these phase increment and phase offset inputs. We can also do amplitude modulation with an extra multiplier at the output. But the endpoint is that we are using this as a built-in self-test. The complete spectrometer design with on-chip test structures is given here. It is a little bit tiny, so let's go into details. So our goal is to try to test every individual block. For that, we can stream in 8-bit parallel data into chip and stream out 8-bit parallel data out of the chip. We can also stream in serial UART data and stream out UART data. Once we stream in certain data, we can send it to input of any of these sub blocks. For example, in split 1 can go into the FFT directly and through this multiplexer, and then we can take data, the output data here, and send it to either to the UART or to the parallel port. In this way, we can assemble any configuration and do any kind of tests. Since the Caravelle test harness is providing us wishbone bus, and we are internally using XE4 bus for memory map, for writing the memory mapped configuration registers, we are also using a third-party wishbone to XE bridge. Regarding the linear sorter, the many digital signal processing applications require hardware sorter implementations. Some of them are radar sorter systems, nonlinear image filtering, etc. So the main operating principle is that on every clock cycle, we are receiving a new data input value, and we are discarding some of the values that are already in the sorter with an invariant that at every clock cycle the array that is inside the sorter is sorted either in an ascending or descending order. In that way, we can have three cases. One is that we pump in data and then shift data towards the discarding elements right, or shift them left, or in case that the discarding element is the input element, there is no shifting, just rewriting. This discarding element can be either fixed, it can be the lowest one or the largest one or the median one. It can be input defined, so runtime reconfigurable, where one can change what is that going to be, or it can be the oldest one, so the one that spent most of the time inside the sorter to achieve a FIFO-like behavior. A systolic array of processing elements to realize this is given here with an internal organization over there. So input data can be either fixed point integer or just unsigned or signed integer. We can have internal. We have a counter which which counts and does the supporting for the FIFO generation. Similarly to the spectrometer, we are also writing over the bus the control and status registers. Test structure is also pretty similar. Just we have included 3 instances of 24 values each. One is with fixed discarding element, runtime reconfigurable discarding element, and the FIFO-like discarding element, and the same parallel input-output and UART input-output are valid here. After running the flow, we obtained the following layouts. On the left-hand side, we have a spectrometer layout of the full chip, and on the right-hand side, we have a linear sorter, which is somewhat smaller design. User project area is here. The rest is the Caravelle test harness part of the chip. This is almost 10 square millimeters. You can see that this is more than 50% filled, even though it is only 1.7 square millimeters of reported post-synthesis area. I have to admit that this was one of our mistakes. We have done the synthesis of the whole user project area at once. So our netlist, Verilog netlist is several megabytes, and we synthesized that. This hasn't been a good idea, but we'll see how it works. What are the lessons that we learned? Well, first, that open lane works just out of the box. However, it took more than 50 hours to go through full flow and produce the GDS. This was not on a laptop, but on a decently powerful server. This is also because we have really pushed it to the limits with such a large design. It would be better that we have split our design into smaller macros. First DRC and LVS clean designs were consequently obtained just 3 days before the actual tape out date. This hasn't left us much time to tweak the generator parameters. We had just one more trial, and this is the result of that trial. We didn't achieve a state-of-the-art performance. We didn't expect to achieve it. What we achieved is a relatively slow clock speed, 20 megahertz, with period of 50 nanoseconds. A relatively small design, just 128 points FFT was made with appropriate accumulator. And as I have mentioned, the spectrometer is a little bit larger, and it is 1.7 square millimeters of post-synthesis area, which gives several square millimeters after post-placement and routing. In expectation of PCBs, we have done verification, of course, before the tape out. Extensive chisel, block, and system level tests were performed. RTL level, Verilator, and Icarus simulations also seem to work fine. What we didn't do quite extensively, but just rudimentary gate level simulations are started, but more time should have been invested in this. Once we get the chips, we expect that characterization efforts are relatively simple in an aspect that we do not require some fancy and expensive equipment, just a simple voltage source to provide the supply, clock source, and pattern generator to drive the circuits, or use the built-in cell test, and just a logic analyzer to observe the outputs. All this can be done with a low-cost FPGA board too. We are very curious to see if the design works, and if it does, what is going to be the maximum frequency that it works on. Our future plans is, well, for short term, we want to do minor tweaks. We want to use smaller hardened macros of our instances and thus try to increase the clock speed, say to 50 or 100 megahertz, and to reduce the running times of the flow. We want mandatory to include SRAM cells, which weren't ready for MPW-ONE. In this way, we are planning to replace large shift registers, which consume tremendous amount of space, with smaller blocks, and thus pack larger FFT lengths like 1K or 2K in the same area. We want to add the windowing function and CFAR processor to detect peaks. This would be realistic for MPW-3. Midterm goals, we want to include a clock generator, some kind of a synthesizable digital PLL frequency multiplier on chip. The current one is FLL, as far as I'm aware. We have experience with this, and we can do it, let's say, in MPW-5. We want to get our hands dirty with analog and integrate some high-speed LVDS receivers or transceivers to be able to capture serial data from front-end circuits like ADCs or RF front-ends or radio front-ends, radar front-ends. And for the far future, we want to base our SoCs on more powerful RISC-V cores. PicoRV32 is excellent and fine, but it is a microcontroller type design, and we would like to use something stronger if possible. That's why we'll probably try to exploit rocket chip generator from Chips Alliance. In addition to that, in addition to range processing, we would also like to process target's velocity and angle through Doppler and MIMO radar techniques. So the common ground to all of our plans is to try to participate in as many MPW shuttles as possible. And even though I was presenting this is not an individual effort, but rather a team effort. These are the guys that have done all the work and that have hands-on experience. I'm really proud of my team, Maria, Nicola, Dejan, and Vukan. Some of them are looking for PhDs, so be sure to grab them before someone else does. And at the very end, I would like to thank the whole Skywater PDK community that is on Slack for their time and selfless help. Also, eFabless team and other MPW-ONE participants for pushing us and not to give up, although there were times we were close to doing that. Finally, this was free lunch for us, but we know somebody had to pay for it. Thanks Google for paying for that one, and thanks Neulich for paying our salaries to work on this wonderful project. So overall, this was unforgettable experience. We would go it through again, and we hope we are going to go through it again. Thank you once again, and I'm open for questions.
Hi, Vladimir. Thank you very much for the presentation.
Thanks for inviting me.
You have a very great background already, right? So can you say like how many tape outs you did before?
Yeah, so quite some. I did my PhD in Delft. There I had some. Then I was for a postdoc in Vienna. Over there I had 2, and I was a postdoc in Berkeley. There I had every 6 months one. So
So you're quite experienced. So how does it differ this time for you? Is there a difference? And I think you observed something like around OpenLane that it's not right there yet, where proprietary EDA tools are maybe. So how was the overall experience, and what nitpicks are there?
the overall experience is great. Of course, we cannot expect that something that is given for free is immediately going to be as good as something that costs millions. But it is getting closer, and some things are even better. It was our mistake that we tried to synthesize and place and route the whole design at once. But yeah, that's our problem. In the next run, we are going to fix it, and we'll give you a better feedback if it works.
So you will use macros then to separate the blocks?
Definitely.
Yeah,
definitely. It would reduce the runtimes, and it would also probably increase the maximum clock frequency that we could achieve.
Oh yeah, that's interesting. So you think like block-based macro design, like the clock base is assumed to be higher than that you can achieve compared to a fully synthesized design?
Yes, because that's what I reckon is that if you have the whole design spread out over this 10 square millimeter of area, then there are timing pads that probably cannot be met, and the slack on those timing pads are going to be bad. And if one design is pretty compact and close by, then probably you can get it to run faster.
Excellent. So did you already do some analysis after you submitted the design to see like what the expectations can be from the chip?
Yeah, it's to be honest. So the design was submitted late December. So then was this New Year and Christmas holidays where we restarted and rebooted, and immediately we got popped up with new projects and new things. So just a little bit of new simulations we have done, but we are waiting for the actual measurements to prove the things.
So what's your gut feeling? Do you have some bets in your team already? Does it work? Which frequency?
Yeah, we believe it will work. Since the simulations are working, we bet it will work. And it's interesting. The default OpenLane flow does the synthesis in the typical corner. Usually we are aiming for the worst corner synthesis. So then we are expecting this higher. If we do the synthesis in the worst corner for 20 megahertz, we would expect it to run, let's say, on 25. But since here it is done in the typical corner, I really wonder what is going to be the maximum operating frequency.
That's interesting. So you're using Shuttle, right?
Yeah.
Did you get accustomed to it while you were in Berkeley, or is it your first design that you're doing with Shuttle?
Yeah, actually, I was in Berkeley 2013 and 2014 and 15, just around the time when Chisel was incepted. So I started using it there, but it was still Chisel 2. Then I got back and started using Chisel 3. But my team is the one that really mastered it. I'm just giving the directions and trying to steer them on the right path. But they're mastering it. I believe they like it. And I really believe, maybe not in Chisel, but in some kind of a Chisel-like language, the future of IC design is going to be. Well, I can, if I dare to say, I think that these EDA tools are running through the same processes software tools have run 50 years ago when we switched from assembly to C. So it is similar process from switching through from Verilog to some not higher level synthesis, but let's say design generators and libraries like in Chisel.
So I think it's a lot about productivity, right? And it gets
exactly an agile design flow. So you are going to invest a bit more time to make a generator than you would invest to make an instance. But once you make the generator and you verify it, you can reuse it multiple times, and the investment will pay off eventually.
Mm-hmm. Yeah, it's really interesting. Let me just double check the questions. So you said you're looking into LVDS somewhere in the future, which is great, I think. Are you tracking just by coincidence if anyone else is already? I think I heard someone mentioning today that there's more analog in the MPW-2.
Yeah, there was actually an LVDS on MPW-ONE. Mohammed will say that better. I also I've noticed that, but I didn't see design files. I just saw the layout, so I cannot really examine it. In MPW-2, there are more analog blocks, and we'll examine them, but after they are silicon proven.
Yeah, I think that's a good decision, right? So there's a question from the audience. Do you plan to connect the FFT with an antenna after amplification to stress the test module? And would you like to be first to implement and actually utilize RV128i? Which is on a longer timeline than you probably.
Yeah, let's do the second part. So RV128 is not on our goal list. It is probably for some warehouse computers where you need to test large memory spaces where 64 bits are not sufficient. And for the antenna, yeah, it is a nice proposal. We plan to attach an ADC eventually. And from the ADC, we can go anywhere else. I mean, we can go to RF front-end, radio front-end, radar front-end, directly towards the antenna on some lower frequencies. Yeah, let's make this first thing work, and then we'll see how we're going to go from there.
Yeah, I really like your attitude. If nobody else is doing it, let's do some ASICs. That's good, and I think it's a great thing that so many people can just get really hands-on, and like it's much more approachable. It's like, and everything that you described fits in the picture, right? It's the mix of productivity, accessibility, and hopefully success, right?
Absolutely, and I believe it is good for us that we entered in these first shuttles, because I believe that there is more space in first shuttles. Not so many people are involved. I believe MPW-5 or 6, there will be like 1,000 designs competing for the place.
Awesome. So let's get the others back in. Just Steve said, "No, when you have a gimbal controller." And maybe we can just do a quick closing round because we are a bit over time because of the technical issues. Once again, sorry to everyone. We will upload the videos individually and edit this to the minimum, which is the interviews, and link everything together. Matt is helping with it. Thank you very much already. Maybe as a quick closing round, like, would you do it again? Which I assume everyone says yes from the interview so far. And is there any like tips you want to give out to people, like some recommendations who want to get into it, like maybe from your individual backgrounds, right? If you're experienced designer, it's different than from coming from different background. Like, is there any recommendations you would give? If people want to target this Friday, it's probably very ambitious, right? But even for the other ones, like, yeah, maybe you can start, Matt.
I would just say jump in. Don't delay. Just take the opportunity and get involved. It's not as hard as it seems.
Awesome, thank you. What about you, Steve? I think for you it was the longest path from the beginning, right, to get to the chip, but it seemed you were very successful in a very short time. What would you recommend to people that are not from the field?
I'd say, in retrospect, and Mohammed told us this, gate level is the make or break. So, you can de-risk so much by just getting a good gate level simulation, regardless of whether or not you're
place and route and densities and all those stuff match up. So do the gate level. Absolutely.
Awesome, thank you. Tristan, what about you? Oh, sorry, you're muted, I think. Can I unmute you?
Sorry. You should start with a simple design and then make it more complex. Initially, I was very ambitious about what I wanted to do, and then I have to simplify it a lot. So I would, as an advice, I would encourage to do the opposite. Start simple.
And finally, Vladimir, I think you already said start with macros. Tristan did right.
But I will also agree with Matt on this. On the Slack channel, I read it, well, maybe 9 months ago, that we are witnessing something that Linux world went 30 years ago. So over then, Linux was also small. It was, some people are like the five of us chatting about it. But watch it now. So I believe in 30 years, the same thing will happen with open source and EDA tools and the whole process. So the sooner you jump, the better position you'll have it for the next 30 years.
Awesome. So I think we should all have a quick follow-up after you got your ships and have been successful. I really hope everyone gets good design points out of it. As I said, we will re-edit it a little bit for the inconvenience we had throughout the presentations. Sorry again. Make sure to tune in next week. We have the presentation from John Volkant from UCSB about OpenPython. And thanks again for your great work. I think it's even more important than Google paying for it, that people actually use it and demonstrate how accessible everything is. Thanks a lot. Great work, everyone. Have a good day.
Cheers.
Thanks, Stefan.
Bye. Thank you.
Bye.